Hi, good morning, and welcome to the ZP vlog and podcast. And I actually should say, no, welcome to the ZP Developer Zone. We do the ZP Developer Zone every Thursday at 8 a.m. London time. It does get a little bit messed up when we're doing things like travel, etc., which was last week. But we do actually do a vlog and podcast, and we do that on Sundays at 8 a.m. But 8 a.m. London time, we try to do this webinar once a week, really to answer technical questions that have come in during the week. So let me jump straight into it and say we do have the ZP Academy. We did have some sign-ups this week, so thank you for anyone who signed up to the ZP Academy. There are at least 2 free courses on the Academy. There is the webinar. This is, for example, a webinar. We do collaborations. We do have PhDs that, for example, being advertised at Swansea University at this very moment. We do have jobs. We have been hiring on LinkedIn. You'll notice some people from USN, University of Southeast Norway, recently. We do have our ZP Developer Zone, and we do have our workshops. So I always try to be efficient with time. This week it's a little shorter. It should only be about, let's say, 20 minutes. If you see a link pop up, then I've already posted the link underneath the video, and that will give you so any links that pop up, I think they're useful because we do have our workshops. So there's a couple going on in at the end of June, one in Norway and one in Coventry. The questions that have come in this week are sensors for urinary tract infection. I will discuss that quickly. Making sensors for 16S RNA. 16S RNA is a sort of really molecular markers for bacteria. Also some questions around sodium and potassium, and some Super Nernstian behaviour that somebody's observed. The behaviour is actually not Super Nernstian, but I'll explain where that behaviour is actually coming from as well. And then also microbiosensors for neuroscience. Somebody's got some sensors from a company called Sarissa. Sarissa went into liquidation. ZP bought the assets, took over the site, hired the people, and we continued the product line. And I'll also talk about that because somebody's got one of the old Sarissa products. Again, if you see a link pop up today, then that's already underneath the video and it'll just take you straight there. So thinking about sensors for urinary tract infection. When you've got a urinary tract infection, you can sometimes detect the sort of bacteria itself, or you can detect biomarkers for a urinary tract infection. It's sometimes easier to detect biomarkers than to actually detect the bacteria itself. Though I realize that question 2 in this webinar today is actually asking the detection of 16S RNA. 16S at least. 16S is a molecular, it's part of the genetics of bacteria, and so it's a sort of specific test for bacteria, but it's quite complicated to do those kind of molecular assays. I prefer biomarkers because biomarkers are often excreted by the bacteria, for example, and therefore are sort of in the liquid phase outside of the cell and are easier to detect. So we do have things like purine sensors. So apparently purine in the urine is in the urinary tract is an indicator of bacteria, but I'm not certain about the clinical acceptance of that. I think it takes a sort of a clinical study to, unfortunately, not a very nice clinical study, where you measure purines versus people who've got urinary tract infection and make sure that there's a strong correlation between these two things. I've also put ATP in here, adenosine triphosphate. I know that ATP is, I think, is an indicator of cleanliness, let's say. So I know that in many applications, people will swab down surfaces and they'll have a color test, and it will often be for ATP. So ATP, I think, is a marker for bacteria. So just kind of highlighting things that we have on the shelf when it comes to purines, when it comes to biomarkers potentially for urinary tract infection. We can get quite involved and actually do assays that were based on sort of immunosensors. An immunosensor would be kind of like an antibody that was specific to a bacteria, and it bound, and that binding was specific. problem with sometimes with that kind of approach is that you can be essentially too specific, because bacteria come in all sorts of species, variants within those species. So I do slightly prefer biomarkers, but let me go forward slightly now anyway. In terms of purine and ATP and many of our sensors, we actually have a really nice workflow developed these days. This is off the shelf materials with us, so we can give somebody an MVP, a minimally viable product, really quickly. And what I mean by that is, we have sensors, so purine, ATP, for example. We have the sensors themselves. We have the apps. The app will, what happens is the app reads the QR code. The QR code says, right, this is that kind of sensor. The app loads up the right method file. The sample goes on the sensor. The meter knows what method file to run, and the sensor's specific for that analyte of interest. And essentially, the data goes to the cloud, and we're able to give a reading. Now, in the terms of urinary tract infection, there's all sorts of parameters. It could be something like CFU per volume, colony forming units per volume, but the units are something that fairly okay to be able to change those kind of things. But it's just to say that urinary tract infection, it's sometimes better to think about the biomarkers rather than actually specific bacteria. But I will actually talk about specific bacteria in question number 2 today. But that said, everything is in place for at least for purine and for ATP, at least to do a minimally viable product. And I just bring up that workshops again, just because we do cover this kind of questions and IVD development, in vitro diagnostic development, in our monthly webinar workshops, rather, that we do hold at either in the UK or Norway. And I think the one in Norway is more useful in this particular inquiry. And if you see a link, I'll have already put it underneath the YouTube video, let's say. Somebody wants to detect 16S RNA. I'm pretty sure, though, I remember this, that 16S RNA is, I think I've done it in the context of E. coli in the past, that it's a marker for E. coli. And we've actually done this kind of work where you've got essentially sort of molecular assay and using ferricyanide as the indicator molecule. Again, if I put a link there, it's because I'm sort of saying, this is the product, or this is the useful material that you should have a look at. So that link is already underneath this video. Reason being is we're selling like a sheet of 300 gold electrodes. They're what's called perforated, which means you can just pop them out of the sheet. And we do sort of like 300 of them for like 500 euros. So it's just over a sort of euro per sheet. Per sensor, which is pretty low pricing. The way we do this kind of work is, we'll take a gold electrode, and I suppose I should have been very explicit here, actually. We have a cleaning solution for gold electrodes, and I didn't spell it out here because with gold, whether you get the gold from ZP or you get the gold from another vendor, which I hope you wouldn't, but if you do, gold tarnishes really quickly. So we always activate it just before use. Activation basically means cleaning. We often use something called MCH, which I think I think it's methylhexanoic acid. So methylhexanoic acid, sort of on one end of the molecule, there's a thiol group or a sulfur atom that bonds to gold, and then the other end of the end of the molecule is a carboxylic acid, and you can do I call it an amide coupling, where you kind of, that carboxylic acid will couple with an amine on the in this case, because it's an RNA, you need to have a sort of a strand of RNA that's got sort of something like an amine group on it that we can couple to. When I say we, you can couple to, but we often do these kind of assays using self-assembled monolayers. But it's important that you actually get essentially the gold cleaned just before you use it. We actually do sell a solution for that, but I haven't linked to it in this video today. We do what you described, which is we call it a kind of capture probe of RNA. It captures its complementary strand, forming a duplex, and we are interrogating that surface essentially with ferricyanide, exactly what we do. And the binding changes the surface, and we pick it up using impedance spectroscopy. I really think that the workshop, if you're new to this, unfortunately I know that these people are inquiring from essentially the other side of the globe, so it's a little bit more tricky for you, but I think the workshops would actually be really useful to you. I do understand the travel problems, but it's literally not that easy to explain. Well, it's easy enough to explain, but there's probably a lot of detail, but we do cover this in quite a lot of detail in our workshops anyway. Take a gold electrode, clean it and activate it, put a thiol layer on there, a self-assembled monolayer. Then you have to do a coupling between the RNA capture probe and the thiol layer. Then when it binds, we then read that binding using a solution of ferricyanide, and we often use impedance spectroscopy. It works really well. I sort of show here that we construct what's called an equivalent circuit, and we look at something like the charge transfer resistance from the equivalent circuit versus concentration. I mean, this is kind of classic literature stuff. The potentiostat, obviously I've got my bias, so I'm going to link to the EIS potentiostat that we would use. And I also want to just highlight something called Julie, because, and hopefully I have put a link to this video as well, that Julie is quite clever, because what it will do is, if you give it a Nyquist plot, which is something you can generate when you do an impedance spectroscopy experiment, it will actually suggest an equivalent circuit for your data, and it will even tell you where it kind of got the reference from. So Julie is quite useful if you're sort of new to EIS and you need a bit of a guidance on it. But we do cover this in our workshops as well, and there is a video, and I will have put the link underneath the video as well. So far we covered 2 questions today. I've kind of said that, look, urinary tract infection, you can either go after the bacteria itself, which is kind of what this second question is all about, but these are not easy to roll out assays. Biomarkers are better. If you found a colorimetric strip that is a good let's say test for urinary tract infection, whatever they're testing on that strip, that's a good indicator of what you should be doing electrochemically. And if we know what those, let's say, strips are testing for, then we can probably reduce that to an electrochemical test. And we do actually have quite a platform in place in terms of apps, connectivity, electronics. We have obviously the electrodes themselves, and the electrodes just need to be functionalized to be specific to the analyte of interest. In terms of doing a sensor or an electrode for 16S RNA, gold electrodes are good. Activate those gold electrodes before you use them, then put the SAM layer on them. Then you have to couple your RNA capture probe. Then you can put your RNA target in there, and then the coupling can be read using a solution of ferricyanide, and the sort of change in the impedance spectrum is a good indicator of that binding. We do that quite a lot. It sort of works quite a lot. This is that kind of work that we've been doing, in fact, and you can hear here the Nyquist plot changes quite well. Somebody is using our sodium and potassium sensors. We do have a sodium sensor and a potassium sensor. They're really good these days, and actually I can see they're really good because the person who sent me the data has really good data, really quite nice. So just a couple of links to the products we're talking about, and then we're going to talk about I'll just bring this up quickly because actually we do cover ISE, ion selective electrodes, in these workshops as well. Question number 3 is about, I'm still on this sodium and potassium. So this is their data, so you can actually see how really nice this is, that they tested at 0.1 millimolar, 0.5 millimolar, 1 millimolar, 10 millimolar, 25 millimolar, 50 millimolar, 10 millimolar, and then so this is their kind of raw data as they've essentially titrated in increasing amounts of sodium onto the sodium sensor, and then they've analyzed their data. They've done it versus the log because they understand this is a sort of log relationship. They know that there's a sort of an equation that helps model this, which is the Nernst equation, so they understand all of this, and they have a kind of slope of 100 millivolts per log of sodium. that looks pretty good, apart from the sensitivity, or the gradient here is twice what they're expecting. So the question is, what's going on here? They describe it as Super Nernstian. As I say, this is covered in our workshops. What's actually happening is they have a sodium sensor and a reference electrode. They're adding sodium ions, and as they add sodium ions, the potential changes. Now that change in potential is being measured relative to reference. Now what they're doing is they're adding sodium chloride. So in fact what's happening is their working electrode is changing potential and is kind of going in a, let's say, positive direction. At the same time they're adding chloride, and their reference electrode is also changing. So rather than just kind of getting this 50 millivolt change because in this example, because the working electrode responded to an increasing sodium, what they don't know, but I'm telling them now, is actually your reference is changing because you're testing with sodium chloride. So in fact you get two changes. The sodium electrode does this, or the sodium working electrode does this, and the reference electrode did this. So you end up getting twice as much signal as you otherwise expect. Half of that of your measured signal is because of the sodium change, and half of it is because of the chloride change. So essentially I showed it here that, rather than you getting a slope of approximately 59 millivolts, you've actually got an additional part of the signal which came from the chloride, and that's why it looks like you've got more like 100 millivolts, and it's not Super Nernstian. It's because the silver chloride electrode is responding to the chloride ions. You have a similar story with your potassium electrode. That beautiful data. I mean, look at that. It's really solid the way it changes. It's really good. And you obviously extract the information by plotting it versus the log of the concentration, so all is good. And you have a really similar slope. I think here your slope is like 110 millivolts, which if I divide by 2 is about 55 millivolts, which is very, very close to the 59 millivolts that you would have otherwise expected. And it's the same thing, that you have a potassium sensitive working electrode and a chloride sensitive reference electrode. Now we do have solutions for this, but I'm not going to bring up those solutions this week. I'm just going to explain this week why you're getting what you're getting. They have a third question. Why is my sodium sensor more sensitive? Why is my potassium sensor more sensitive? And then their third part of their question is, I'm testing the sodium sensor with potassium and it's responding. And so I'll show it here. So on the left hand side here, this is a sodium sensor being tested with potassium chloride, and they get a signal of approximately 150 millivolts when they go from 0.1 millimolar to 100 millimolar. Now if they test the sodium sensor with sodium and go from 0.1 to 100 millimolar of sodium, they get 350. If I do the ratio of these two things, it says that they're for every molecule of potassium they would get 40% of the signal that they would otherwise get for sodium. So that sort of tells you that it's not as specific as they would imagine. It's actually more selective. But this is actually the case across the blood gas analyzing world, because the reason that it doesn't cause a problem is because potassium in clinical and sort of physiological samples is approximately 5 millimolar, whereas sodium is 135 millimolar. So the fact that the sodium sensor is sensitive to potassium, and you could argue it's quite sensitive. In fact, it's sort of it has a sort of sensitivity of about 40% to potassium relative to sodium. But the fact is, sodium is by far the dominant cation in, let's say, human physiological clinical samples, that actually it doesn't cause a problem. And the kind of science that we're using is really similar to what's actually used in real blood gas analyzers, let's say. So in fact, this argument that the reason it doesn't then cause a problem in the real world is because actually potassium is really low. So if your sodium sensor is slightly sensitive to your potassium, it doesn't matter because your sodium ions are an order of magnitude greater in concentration. In fact, it's 2 orders of magnitude, because it's not 50 millimolar, it's 135 millimolar, which basically means it's 2 orders of magnitude greater. So, and I just want to bring up, I have a reference here, or rather I have a page written on this, and just to give you a sense that there is something called the kind of sensitivity, I think it's called the selectivity factor, which says my response to ion X versus my response to ion A. And the sodium sensor, in the literature, they say that actually a sodium sensor will show about a 60% response to potassium, whereas in fact your data shows for us it's actually more like 40%. What's interesting is the potassium sensors are actually a lot less sensitive to other cations than the sodium sensors, and it really just comes down to the biochemistry of the sensor itself. So sodium sensors are sensitive to potassium, but actually potassium clinically is so much less concentration that it doesn't cause a problem. Unfortunately, this is a fortunate thing, the potassium sensors are quite insensitive to sodium. So my suggestion is not to challenge, but to sort of check some of what I've said today. Test your sodium sensor with sodium phosphate. The reason I'm saying sodium phosphate is because then you don't introduce an extra chloride ion. What you will end up doing is introducing a dilution. So you have to think about when you add that sodium phosphate, you'll have to account for the fact that you're going to be diluting that chloride every time you add a bit of material. But the reason I'm saying this is when you add sodium chloride, obviously you're shifting the working electrode and the reference electrode. If you add sodium phosphate, you're only shifting the working electrode. But I think we don't just add sodium phosphate, we actually understand that we could end up diluting slightly the chloride, so we have to actually substitute for that, or compensate rather for that as well. So try testing with your sodium sensor with sodium phosphate, try testing your potassium sensor with potassium phosphate, and just out of interest, I've argued just now that your sodium sensor is showing activity towards potassium. You could also try testing your potassium sensor versus sodium, and I think you'll find out that the potassium is, if it's in line with literature, is less sensitive. Question number 4 is really about Sarissa sensors. So Sarissa was a great company. Unfortunately, they went into liquidation. As I say, ZP bought the assets. They make micro electrodes for people doing neuroscience work. They have something called their null electrode. Their null electrode is essentially sort of described as a blank. It's not meant to be active towards any particular analyte. It's just measuring the background signals. So they have a couple of these, and they're a bit concerned. I might put a link again. They're a bit concerned that, and also it's probably worth saying we're going to have a workshop specifically on neuroscience biosensors in Coventry in September, and we're also doing it in conjunction with Warwick University. That's the link. They've sent me an image, so they've shown me the very tip here. They think that's a shroud or cover. It's actually part of the sensor, so don't be put off by this. This is really as part of the sensor. If it's not working, it's because you need a reference electrode to go with it. This is essentially what you call your working electrode, and you need a reference electrode to go with it. But that shroud is not a problem. That shroud is, or that material is part of the sensor, so it's not a sort of essentially a big issue. So let me sensor for urinary tract infection. If you have a colorimetric urine stick and it's detecting different anions and cations or different small molecules, those can be translated into an electrochemical sensor, and that means you do enter the digital world, and we do have a stack of technologies to do that. That's 16 sRNA. That's a real classic. I would just start with a gold electrode and using impedance spectroscopy, activate that gold, clean that gold before you use it. We do have a cleaning solution on our website for that. We do use 6-mercaptohexanoic acid often as our self-assembled monolayer, and then we do couple using, I think, EDC coupling and amide bond coupling to the antibody, to the RNA in your case. It's the RNA. I didn't say it, but you also sometimes have to, you do have to use a blocking, maybe you don't have to use a blocking agent. I was going to say we use BSA, bovine serum albumin, to stop non-specific binding. But hopefully the SAM layer might actually prevent that. And reading with ferricyanide is definitely something we do. Our workshops would be particularly useful to you because we really get into impedance spectroscopy in biosensing. You do not have super Nernstian behaviour. You have very good behaviour. It's just you're showing sensitivity, and this is question number 3, both to the cation of interest, but also the reference electrode is shifting. Now, if you want to know how to fix that reference electrode, re-ask me the question, and we will in an email, and we'll go over it next week. And then number 4, your microbiosensors for neuroscience. Yep, we did take over Sarissa. We do carry on making their product. We did have a look at your image. That shroud is meant to be there, and it is part of the construction. So it's 8:27 a.m. London time, so it just gives me time to say thank you. If you have any questions, and if you've got questions that come through the YouTube channel, I do try to stay on top of them, but if I'm not answering the questions, and I said I would, just remind me through the YouTube notifications or chat, and I will honestly try and make sure I remember to answer those questions. So thanks very much. I hope everyone has a good day, or at the end of the day if you're on the other side of the globe, and we will speak to you soon. Okay, thanks very much.